This video covers Chapter 6 in EE21. So we're going to learn about new passive components, capacitors and inductors. So these are passive components like resistors. Capacitors and inductors are passive components. The circuits we have analyzed so far have been all resistor circuits, and resistor circuits have very limited usefulness by themselves other than learning the rules of electronics and the rules of engineering. Resistors can only dissipate energy, so when current passes through them, they heat up and they dissipate energy. Capacitors and inductors, on the other hand, will store energy. Capacitors will store electric energy and inductors will store magnetic energy. And in general, they do not, at least in an ideal case, they do not dissipate energy. So let's talk about capacitors first. This is a cartoon of generic construction of a capacitor. It consists of a conducting top plate and a conducting bottom plate, and in between is a dielectric or insulating material that's been sandwiched in between the conducting plates. This part right here represents the wires going in and out of the capacitor. This is a cutaway view of probably a ceramic capacitor. So I have just a coating on the outside of it. There's the two leads going in. It goes into the dielectric material, or it goes into the metal plate. And then inside will be the dielectric material that's sandwiched in between. So you could make it square, but I imagine that making them rounded like this is better fabrication practices. So here's some examples of capacitors and also what their schematic symbol is. These are polarized capacitors shown in the top row. Electrolytics, which will have the minus sign marked on the side as so. Tantalum, which I have many examples in the lab that you can look at. And there is even a larger surface mount capacitor package for electrolytics. Then we have some also that are not polarized capacitors, so that they can go any way in a circuit. Typically these are our ceramic capacitors, can also be polyester capacitors. And then there are also variable capacitors. These are the various symbols. If it's polarized, it will have a plus mark on the positive terminal, or sometimes it's just done by this curved side. So the curved side is the minus side, or the lower potential side. Reading the capacitance off of a part is a lot more complex than for resistors. Resistors, you either read the number if it was surface mount or read the paint code on it. In capacitors you have generally three categories. One, numbers are printed on the capacitor like in this drawing. In some ways it's similar to a capacitor. You have first digit and second digit are values, and the third digit is the multiplier. When you see a number like this with no decimal place on it, it'll be in picofarads. So 474 means 47 times 4 zeros, or 10,000 picofarads, and then you'll have to change it to microfarads. The M or G or J or K marked on the package is for the tolerance, how accurate it is. It does not mean mega. And then there will be a maximum voltage listed, so you do not exceed the maximum voltage of your capacitor. Here's your summary of your metric prefixes. There are also capacitors that are painted with stripes on it. In this case it is very similar to a resistor, but the answer that you get is in picofarads. And then there are larger capacitors, usually are electrolytic capacitors, and because their package is larger, their value is written right on the package, and it's usually in microfarads. So capacitors store charge. This is the defining relationship for a capacitor right now. Charge equals capacitance times voltage. So the amount of charge this device will store is proportional to the applied voltage and the capacitance, and capacitance is tied to the physical construction of the part. So here it is a cartoon of a capacitor in the schematic. So a positive voltage is applied to one plate, a negative voltage is applied to the other plate. So this plate is at a negative potential compared to this plate, and then you have this dielectric material in between, which causes a separation of charge, and this charge, if it has nowhere to dissipate, will be held by the device. So the amount of capacitance, I said, was dependent on the physical geometry of the device. In particular, it depends on the area of the metal plates, that's A right here, the distance between the plates, D, and this value, it's a Greek letter epsilon, which is the permittivity of the material. So permittivity is a material property. This material that's sandwiched in between the plate, even air will be make a capacitor, but in general it's something like mylar, plastic, paper, or an electrolytic, what's more like a gel. And it has a material property, a permittivity associated with it, which you can look up on tables of material properties. Permittivity is in farads per meter. So now we want to be able to use our capacitors in a circuit, so we have to understand what the relationships between current and voltage for the capacitor, just like we have for a resistor, a relationship between current and voltage. So we'll start with this defining relationship that the total charge is capacitance times voltage. If I differentiate both sides with respect to time, dq dt equals c. Now capacitance is a constant depending on the physical geometry of the device, and then dv dt. So dq dt, that's charge per second, coulombs per second, that's current. So down here I've directly shown that that's equal to current. So current in a capacitor equals the capacitance times the time rate of change of the voltage, or dv dt. So this is the differential form of what's happening between the relationship between current and voltage in a capacitor. We would also like to have an integral form, so I'll start with the differential form. Rearrange the terms in the next line here, and then solve for the voltage. It's nice to have voltage by itself, or it's nice to have current by itself. So voltage as a function of time is then the integral from negative infinity up to some time t of I of tau d tau. That's my placeholder variable there for time. But in reality, we don't necessarily know what the charge on the capacitor was at t equals minus infinity. So really we know starting at some time, maybe it's t equals 0. Then we want to find the total voltage that the capacitor has charged up to. So then we have a relationship like this from time 0 to the time of interest. Integrate the current plus the initial voltage that is sitting on the capacitor. So if the capacitor is already at 5 volts and I apply 10 volts to it and I charge it up for some known period of time, I can figure out what the total voltage is on that capacitor at some moment in time. Energy and power in a capacitor. I stated at the beginning of the presentation that energy is not generally, or power is not dissipated by the device, but it can store energy and release energy, and energy released over a period of time, it would be a power supplied. So power by definition is current times voltage. Here's the definition right there. So I can substitute in what current is, dVdt, C dV dt, and that's the relationship for instantaneous power that a capacitor can supply. Looking at the units of this, since the book neglected to talk about the units, I have C, V, dV dt. Capacitance is in farads, volts is still volts. dV dt is volts per second. Do some unit cancellations. Now I have coulombs. I have I'm left with well, farad is a coulomb per per volt, and that lift with coulombs volts per second. A coulomb is an amp second times volts per second still, and which ends up after some unit cancellations is an amp times a volt. Amp times a volt is a definition of a watt, which is a joule per second. Energy. Energy is found by integrating the instantaneous power over the total time that the power is being supplied to the circuit. So doing the math here, you end up with this relationship that the energy is 1/2 CV squared over the time of interest. Units on this, we are integrating a joules per second over time, which will end up being units of joules. Joules is indeed energy. How do capacitors behave in a circuit? Here's a behavior summary. These are really actually important concepts to remember about a capacitor. So VC means voltage on the capacitor. If the voltage on the capacitor is constant, no current is flowing. An example of this is a fully charged capacitor. If I have a circuit and I've waited for a long time until the circuit behavior is stable, this means, actually, we'll learn about it more in the next chapter, but we're not in the transient behavior mode. We're in the steady state time when everything is a constant. And if the capacitor is fully charged up, then it's up to its full voltage, then it has no current flowing in it. If no current is flowing in it, then a fully charged capacitor is an open circuit to DC in the circuit. Over time, the voltage across a capacitor is continuous. The voltage across the capacitor cannot change abruptly, meaning it can't be +5 1 second and -5 volts the next moment in time. That cannot occur because that would imply infinite current, and that doesn't happen. Do note that the current in the capacitor can change abruptly. For example, if I have a fully charged capacitor, and it's not doing anything, it's sitting there as a fully charged capacitor, and I suddenly connect something to it, that capacitor will discharge into that load, and the current can initially be extremely high. So we've gone from zero current to instantaneously a very high amount of current discharging into the circuit. This is what makes capacitors very dangerous in circuits. If you have something that has a large capacitor in it, such as an air conditioning unit or welding equipment or an old-fashioned TV or a cathode ray tube, they have large capacitors in them that store up a large amount of charge. If you were to touch that with your fingers, you can kill yourself because that current will instantaneously discharge into you. Well, as fast as the resistance of your body will let it. So, okay, so voltage cannot change abruptly in a capacitor, but current can. An ideal capacitor does not dissipate energy. It stores it and releases it. So it's not going to give off heat either like a resistor does. But in reality, nothing is ideal, and there is some parallel, it's like leakage resistance, we call it. So if you were to model a non-ideal capacitor, you would have a capacitor in parallel with a small resistance. Excuse me, large resistance. So let's do a few examples. Some of the examples in your textbook are a little trivial. 6.1, 6.2, and 6.3 are just direct application of a formula, so not very interesting. Well, 6.3 is a little bit more interesting. Determine the voltage across a 2 microfarad capacitor if the current through it is this. This is a very real example. You will see something like that when we do this in the lab. The current will be behaving in an exponentially decaying manner, as this is showing, as this equation describes. So it's something that at t = 0 will be at 6 milliamps, but as time progresses, the current will decay. So that's what this equation actually represents. Go away, time. So just get my pen out. So this is I, This is T. It starts off at 6 milliamps and it decays. So that's what the current is doing in this particular capacitor, I sub C. So kind of strange that the capacitor voltage is initially 0. I would have thought that it was a positive value. So V sub C at time 0 equals 0. So now we have the relationship to apply is V equals 1 over C from T0 to time T. Does it tell me how much long? No, I guess we want it as a function of time. Okay. T0 to T, I of T, tau, d tau, plus, since we're not at minus infinity for time, V at time 0. So now it's a matter of doing the math. It's 2 microfarads. Keep it in pure units, which is 2 times 10 to the minus 6 farads. And the integral we want is from time 0 to T. And then we just plug in the equation, 6e to the minus 3000 T tau d tau. And voltage at time 0 is 0. So we are good there. You just do the math, integrating e to the integral of e to the minus 3000 t is, the integral of that is 1 over negative 3000 e to the minus 3. Whoops, messed that up. It's, sorry. There, I removed my silly little mistake. So we do the integration. Silly little. Every now and then I have a brain fart, we say, right? 10 to the minus 6. Do the integration. Minus 3000 right here. 6 in the numerator out here because I brought out the constant. Integral from 0. Just did the integral, so I have e to the minus 3000 tau, and I'm going from 0 to time t. So your author doesn't even simplify the we simplify the math. It came out to be a 1. All of this together, strategically chosen numbers, comes out to be a 1. And then we have still e to the minus 3000 tau from tau equals 0 to time t, which is e to the minus 3000 t minus e to the minus 3000 times 0, which is, and there was a negative sign out here, negative sign out here, negative sign out here. So that makes that be e to the 0 is a 1. It's negative, so it's 1 minus e to the minus 3000 t. And that's volts. Volts. Okay. So that problem was in your book, so not real exciting, but at least it's using the relationship between the voltage and the current in a capacitor. Other problems that I like, which I'm just going to bring your piece of the textbook over here. Other problems that I like this problem. So you have a 200 microfarad capacitor. That's a gargantuan capacitor. And it says the voltage is doing this. So then it's described mathematically here. I like this equation, or this problem, because yes, you can turn a voltage on or off or switch directions, and so that's realistic to think that the voltage across the capacitor is doing something like that. So then it says, what does the current do? So if you just apply I equals C dV/dt, that's V of t right there, do the little bit of calculus right there, you get the current doing this. So what it's saying is that the current can instantaneously switch. So it's 10 milliamps when the voltage is increasing across the capacitor, and which would be like when the capacitor is charging up, and now the voltage is getting smaller across the capacitor, implying that the capacitor is discharging, and so discharging is reversing the current direction, but look at this maximum value in the other direction of current. So this would be very much like a capacitor charging up, and then this is very much like a capacitor discharging. It's a stored charge. So that was a nice problem. And then this is the other nice problem that I like, that really matches principles that we have to remember about what capacitors do. So it says obtain the energy stored in each capacitor under DC conditions. So when they say under DC conditions, that means that the circuit has been turned on for a long time and nothing is changing in the circuit anymore, and in reality the capacitors have had time to charge up to their maximum voltage, and since they are fully charged and the voltage is not changing across them anymore, there is no longer current flowing through those capacitors. So if there's no longer current flowing through these two capacitors, what does that mean? It means we just take them out of the circuit and put an open circuit right here. Current isn't flowing there anymore. The capacitors are fully charged up. So now all we have to do now is analyze this circuit, find through the rules that we already know how, what the current is here and the current is here, and we have the voltages that are associated with V equals IR for this device and for this device. So that's what we did. The only little trick to this is, well, we apply our normal rules, find the current going through here. There's no current going through this part of the circuit because it's open right now. You have a voltage drop here, and then we have a voltage drop here. It's important to recognize that the voltage drop that's across here is the voltage drop that you see across these open terminals right here. That was the only, because no current flows here, so there cannot be a voltage drop here. So that was the only trick, was conceptually seeing that the voltage across this resistor is the same as the voltage that's shown right there. That's all there was to that problem. It wasn't that bad. So now let's talk about the series and parallel capacitors. Okay, now we'll look at what happens when capacitors are connected in series or in parallel. So the first one we'll look at is in parallel. Here's N capacitors connected in parallel. To analyze this, we apply KCL. KCL applies, Kirchhoff's current law applies regardless of whatever devices you put in the circuit. So Kirchhoff's laws and Ohm's law are true forevermore. So if I apply KCL, I have source current divided amongst all the parallel legs, I1, I2, I3, IN through the capacitors. We know that I in a capacitor is C times the voltage in the capacitor dVdt. Because these are all in parallel, they have the same voltage, so I can factor out the voltage here, dVdt, of the capacitor, and you're left with summing up C1 plus C2 plus C3 plus however many. So the conclusion is that capacitors in parallel add up. Let's look at capacitors in series next. So here are some capacitors in series in a circuit. Since Kirchhoff's laws still apply, we will apply Kirchhoff's voltage law. So the sum of the voltages, sum of the voltage drops in the loop will equal the source voltage. There I've written Kirchhoff's law for this circuit. We know that the voltage in a capacitor is 1 over C integral of the current plus any initial voltages that exist there. So if we do that for our N capacitors that are in series, we get a big long ugly equation here, but the thing that we see that's constant is that there is one constant one constant current in the loop. The loop current is the same everywhere, so we end up with one term of integrating the current right here, and then we have the capacitance factors that we have to sum up. Well, it's 1 over C, so we're summing up all of the 1 over C's. From that we can say that the C equivalent, 1 over C equivalent, is 1 over C1 plus 1 over C2 plus 1 over however many capacitors there are. So this is sort of like the parallel resistor equation, but these are series capacitors. So the forms of the two equations are sort of opposite to each other between resistors and capacitors. And if you have just two capacitors in series, we have this equation. So once again, we can algebraically take a little bit of a shortcut and realize that the equivalent capacitance will be this formula, only when there are two capacitors in series. So now we'll take a look at some of the examples in the book. The examples in the book are not super exciting. They are reminiscent of doing resistors in series and parallel. So this is the first example, and it is talking about, just make sure I have my pen going, find the total equivalent capacitance of this circuit looking in from this direction. So just like if these were resistors, the first thing you would do is look at these two capacitors that are in series. So series looks like the parallel formula. So here I compute their total capacitance. At this point in time, I have a capacitor now in parallel with another capacitor here, in parallel with another capacitor here. So that's what I have here. Since they are in parallel, they just add up. So now I'm down to a circuit that looks like a capacitor here, a capacitor here. This is 30. My pen doesn't work very good in PowerPoint or in PDF documents, and this is 60. So we're down to that much of a simplified circuit right now. Those are in parallel, so we apply the parallel form. Those are in series, so we apply the series formula for capacitors, which has that, sum of the reciprocals formula, and then we get the total capacitance of that circuit. Not real challenging, but it's still concepts that we have to get. And they have a few more examples here, but you're basically just applying, once again, series and parallel formulas to the circuits. So one thing I will note, you've probably noticed it already, but I'll just use this problem as an example. Everything is in microfarads here, so I don't have to make everything be in farads and say 20 times 10 to the minus 6 times 5 times 10 to the minus 6 divided by, etc. I don't have to work the whole problem in farads. If everything everywhere is in microfarads, I can work the whole problem in microfarads and my answer will be in microfarads. Just be careful if a nanofarad or a picofarad is snuck into the circuit, because you have to make sure that you put everybody in the same units for all of this to work. So now let's talk about the next passive component we're going to talk about in this chapter, which is the inductor. You'll see that the inductor in many ways behaves just the opposite of a capacitor, but they also have a lot of similarities. So inductors store energy in the magnetic field, and I'll explain that more here in a moment. Inductors are used a lot in RF applications and in transformers. So we will later study transformers where we will have two inductors in close proximity to each other, and the magnetic field induced in one will couple into the other, and you will have these things called step-up and step-down transformers. So anyway, the defining relationship between voltage and current in an inductor is this. Voltage as a function of time equals L. L is the symbol for inductance, and then times the rate of change of current, di dt. L is in henries. Inductance is units of inductance is henries. Henries is the amount of henries an inductor has is also is a function of the geometry of the device. So here's a general kind of a cartoon picture of the geometry of the device. You have a coil, inductors are often called coils, but you have a wire that's wrapped around, or may just be in a coil around air, but it's wrapped around a center material and current is passed through this coil, and this current will create a magnetic field, which I have a picture of coming up next. But how much inductance this device has is calculated by n squared, where n is the number of turns of the wire. So if it wraps around 100 times, that's 100 squared, times mu, Greek letter mu. Mu is the permeability. Permeability is a material property. It's the permeability of this core material, which could be air, but oftentimes it's a ferrite material. Permeability is a measure of the material to support the formation of a magnetic field within itself. So a magnetic field is going to be formed by current going through this wire, and if I have a material with a high permeability, like a ferrite material, then it will concentrate the magnetic field in the core material. So it will support a higher, I want to say intensity, but it's not really intensity. It will support a higher concentration of the magnetic field in the material. So it's a degree of magnetization that a particular material can support in response to the applied magnetic field, which is created by the current passing through this coil. I am assuming here that everybody has seen this device in physics and that I do not have to go over the field equations that show how current generates a magnetic field. But if I have assumed wrongly, somebody send me an email or tell me, and I will go over the electromagnetics of the formation of a magnetic field inside this device. So the other properties, physical properties of the device that determines how many henries an inductor has, the value of the inductor, is the area, which is the cross-section area of the core material, whether it's air or a ferrite material, and L, which is the length of the coil area. It's a little bit misleading in that picture. So here's a picture of various inductors. As you can see, literally it is wire wound around a core of material. This wire does have an insulation on it. It's often a ceramic material, and many times this wire is called magnet wire. I'll show an example in class, and I'm sorry for my distance student who doesn't get to see all my box of toys that I have. So they are in generally two shapes, a solenoid type shape like this and a toroid shape or donut shape like this with the wire wrapped around it. So back to our defining relationships for an inductor. We had V equals L di dt. If I rearrange the terms, I get the next line in my equation, which, since I have a di on the left and a dt on the right, I can integrate. So I will integrate both sides of the equation. So I will get I on the left, and I'll get this integral equation on the right. It is going from minus infinity to some time t. We often don't know what happened at time minus infinity. So instead we started at time t equals 0, or time 0, which may be 0, but at time 0, and then we'll include the initial value of the current at time t0. So oftentimes we start at time 0, but maybe not, and then we can have the current at time 0, and so then we have a more usable form of the equation. We also have power and energy relationships for an inductor. This power represents the instantaneous power held in the inductor. So power is in watts, which is the same as joules per second. And then if you integrate the power, the instantaneous power at any given instant in time, and if you integrate it over a total time period, you will get energy in the end. So energy, and its units will be in joules. And so just doing the calculus right here, you will get that energy equals 1/2 Li squared. Remember, for a capacitor it was 1/2 CV squared. So they have some similarity, but I have an I here instead of a V here like I do for a capacitor. So that's in joules. Energy is in joules. So behavior of inductors in a circuit. So the voltage across the inductor, which I say VL, should be a sub L, but VL will be 0 when the current is constant. So if the current is not changing at some particular point in time, then there will be no voltage across it, and it will act like a short circuit. That means it acts like a short circuit in the DC, or what we say in the steady state, or after the circuit has been turned on for a long time and no AC signals are happening in the circuit. The current through the inductor cannot change instantly. So remember, in a capacitor the voltage could not change instantly, but in an inductor it's the current that cannot change instantly. So we say that the inductor opposes changes in current. This is actually due to the fact that there's a magnetic field there, and the magnetic field prevents instantaneous changes in current, and it has to do with the way the electrons are being I don't want to say control, but the way the electrons in current are being influenced by the presence of the magnetic field. So an inductor does not dissipate energy, just an ideal inductor does not dissipate energy, just as an ideal capacitor does not dissipate energy. However, energy can be stored in the inductor, and in this case it's stored in the magnetic field, and it is available to be used later. So the ideal inductor has no resistance, but real devices do have significant resistance and also a capacitive component. The resistance part is often called the winding resistance. So now let's look at some examples. Oops, I didn't want that there. So I will take the examples out of your textbook. They are not strenuous, but they have some good points to them. So the first one that I was going to look at is this one. You have a 0.1 Henry inductor with the current given by this equation, T e to the minus 5t amps. The current is in amps. This is really a math equation. It's a matter of saying I have I of t, apply this equation that V equals L di dt, and that you have the known value of the inductor. So it's really a matter of applying rules of calculus, plugging in the formula, and you will get what the answer is for the voltage across the inductor. Similarly, the energy stored just by plugging in the equations is 1/2 Li squared. So I do have to square a function that has a t in it, which should be something that everybody in this class can do, and your answer will be in joules. This time your textbook put the units in, so I was happy. So the other example I particularly liked out of this book right now was this example. We had a similar example with a capacitor circuit earlier in this presentation. So it says, consider the circuit and under DC conditions find I voltage across the capacitor and current in the inductor, and then find the energy stored in both the capacitor and the inductor. So under DC conditions means there's no AC signal present and everything is steady, nothing is changing. So all capacitors have been fully charged up. All inductors no longer have a voltage across them. So you take the original circuit right here, shown right here. You replace the capacitor with an open, because once it is fully charged up, current doesn't flow anymore. And once a steady state condition has been reached for the inductor, there is no longer a voltage across it, and it is just a steady current. Current is not changing, therefore it cannot have a voltage across it, and so you replace that element with a short in the circuit. Then we go and analyze the circuit like we normally would. we find currents, we find voltages, keeping in mind that the voltage that is present across the 5 ohm resistor is going to be the voltage that you measure across VC. So that's what we did here. We found the current first by our normal rules that we have learned. Then I found the voltage across this resistor, 5 times I, and that's 10 volts. That will be the same as the voltage across the capacitor because no current is flowing here. And so I'm essentially saying it's the voltage right here at this node. No current is flowing here. That means there's 5 volts there, and there's 5 volts there, and this is tied to 0, so it will be 0 volts there. I mean, sorry, 10 volts. 10 volts everywhere. Energy in the capacitor, you just plug it in the equation, 1/2 CV squared. You have C, you have V, plug it in. And the inductor, 1/2 LI squared, plug in the numbers, and you'll get energy in both cases in joules. So I do like that equation, this example, just because it emphasizes the fact that at DC, or in the steady state, as we will learn more about in the next chapter, the capacitor is an open with a voltage there, and the inductor has no voltage, and it is a short. Now we'll look at inductors in series and in parallel, just like we did for capacitors and for resistors. So here I have a series circuit with inductors in series. Kirchhoff's voltage law applies here like it does for any other passive circuit. So I write Kirchhoff's voltage law for the voltages in this loop, keeping in mind that there is one and only one current in the loop. I substitute that the voltage is L di dt into the equation, into KVL. The L's factor out because di dt is the same everywhere, and I get a nice equation with the sum of the inductances times di dt. So from this you can glean that the equivalent inductance is the sum of the inductors when the inductors are in series. So inductors in series add. Guess what inductors in parallel will do? So here's my circuit with a bunch of inductors in parallel. So now the appropriate law to apply is Kirchhoff's current law. So the source current equals the sum of all the currents in the branches. But we know that I equals 1 over L, integral of the voltage. So now I substitute that into my KCL equation. So I get big long equation with lots of integrals in it. But what's constant here is that the voltage across each inductor is the same, but it's actually the integral of the voltage. But nevertheless, the voltage is the same across every single inductor that's in parallel. That's a consequence of any of these components being in parallel. So now I can factor out the voltages and also all of the initial currents and multiply times the 1 over L. From this I can glean that the 1 over L equivalent is the sum of the reciprocals of the individual inductors. Looks like the resistor equation, doesn't it? So let's compare all three devices. This is a nice table summarizing everything that comes out of your textbook. So the voltage current relationships, well, voltage in terms of current and current in terms of voltage relationships for both R's, C's, and L's. The power or energy relationships, and then the series and parallel formulas shown for, actually just shown for two devices in series or parallel. What happens at DC? Nothing for a resistor. DC is, that's what we've been doing all along, DC with resistors. Capacitor will be an open circuit, and an inductor will be a short circuit. The circuit variable that cannot change abruptly, in a capacitor it's voltage, and in an inductor it's current. So nice, useful summary chart. So I'm coming up on 45 minutes now for this PowerPoint, not PowerPoint, but YouTube. So some students have told me that my YouTubes get rather long and to keep them under an hour. So I'm going to stop at this one. We have coming up still in this chapter some applications. The applications are good and interesting applications, but I'll make it into a separate video.